Now that we know what a hard problem is and how to show a problem is hard, how do we actually deal with a hard problem? Whenever we are faced with a hard problem, we know that there isn't a polynomial time algorithm, and in effect, there's no efficient way to solve it. So we have to do something else. There's a few different things we can do. We can restrict the input, we can deal with some approximation, we can deal with some randomization, or we can deal with heuristics. Each one of these four techniques is different. To restrict the input means that we're going to restrict exactly what counts as an input, and hopefully this will make the problem easier. In the approximation framework, we're going to develop algorithms that are provable to get good guarantees. This is usually a hard task. To use randomization, we'll say that we'll have an algorithm that's going to occasionally get the optimal solution, but there's some probability that it's not going to get the optimal solution. Finally, in heuristics, we develop algorithms that sort of seem good based on our intuitions, but we don't really prove anything about them, and we just deal with their solutions. We're going to focus on restricting the input and approximations. To restrict the input, we first have to deal, or rather be clear about exactly what the input is. We solve this. We're going to set I as the set of all instances to a problem. Our restricted input is going to be some subset of I, which we're going to call I sub r. We know that, or rather our goal, is to say that we develop some algorithm so that when this algorithm runs on an input I that's inside of our restricted set of instances, that this algorithm is going to return the optimal solution and also run in polynomial time. We've actually seen quite a few examples of this. We know that the vertex cover problem is a hard problem, but in bipartite graphs, the vertex cover problem is actually an easy problem. If we restrict the input to the vertex cover problem to bipartite graphs only, then we can develop an algorithm that's going to return the optimal solution, the optimal vertex cover, in polynomial time. We also saw in a homework assignment that if we restrict the knapsack problem so that all sizes are exactly equal to 1, then we can solve it in polynomial time. This is again restricting the input. Finally, we've seen the independent set, restricted to bipartite graphs, is also a simple problem. And one of the main results that we talked about in lecture is that if we have an integer program and we restrict it to have a totally intermodular constraint matrix, then that integer program is easy to solve. In effect, we solve the linear program and that automatically solves the integer program. All of these are powerful examples of restricting the input so that we can get a polynomial time algorithm. The approximation framework is quite different. Here, how we deal with approximation depends on whether P is a maximization problem or a minimization problem. In the maximization case, we're going to develop an algorithm that we call A tilde that is an alpha approximation. Here, alpha is the guarantee. In a maximization problem, alpha is going to be less than 1. Our approximation algorithm, A tilde, when it's applied to any input, that is any instance, it's going to achieve a solution that's at least alpha times the optimal solution. And we should make sure that this makes sense. Our approximation algorithm is going to give us a solution that's at least alpha times the optimal. Alpha is less than 1. So the guarantee for our approximation algorithm is not that it's going to get us better than optimal, but something slightly worse than optimal. That's why we call alpha our approximation guarantee. Also, crucially, A tilde, our approximation algorithm, is going to run in polynomial time for every instance. This is all for when P is a maximization problem. When P is a minimization problem, we reverse the roles of alpha. Alpha now is greater than or equal to 1, and our solution is going to be at most alpha times the optimal. We won't deal a lot with approximation algorithms in this course, but we did see one example. With submodular maximization, we developed an approximation algorithm, or at least stated an approximation algorithm. This was a polynomial time algorithm that gave us some guarantee rather than an optimal solution. One final note before we leave hard problems. One interesting feature of hard problems is that if we ever focus on a particular instance, we can always consider that particular instance as an easy problem. Suppose that we have a problem A, and it has an algorithm that runs in order 2 to the n time. This is an exponentially timed algorithm, but this is a constraint on our algorithm because it has to solve every problem in A. So we express the runtime as 2 to the input. If we focus on just a particular instance, just one instance that has size 1000, then our algorithm runs in order 2 to the 1000 time. And 2 to the 1000, however large it actually is really just a constant as a function of n. So this is technically polynomial time. This is sort of just a hack. In reality, if we focus on a particular instance, that doesn't mean that that instance magically becomes easy. The hardness of the instance is really just as hard as before. This is just a technical glitch in our definitions.